Introduction to Classical Mechanics. Hello and welcome to the first lesson of our physics lecture series today. We are going to explore the fundamentals of classical mechanics, a core branch of physics that deals with the motion of objects and the forces acting upon them. Understanding classical mechanics is essential because it provides the foundation for all the other branches of physics. Whether you are interested in astronomy, engineering, or even understanding how everyday objects move, classical mechanics is the starting point. Physics is all about discovering the underlying principles that govern the universe, and classical mechanics is where we begin this journey. Today's lecture will provide you with the basic concepts that will help you navigate this fascinating world of forces and motion. Basic concepts of physics. Physics is a study of matter, energy, and the interactions between them. Every single thing we encounter in the universe, whether it's a book on your desk, the earth spinning around the sun, or the particles in your body, is governed by the laws of physics. The goal of physics is to understand these laws and use them to explain the behavior of everything, from the smallest particles to the entire cosmos. But how do we approach these massive problems? We break things down into smaller, manageable concepts. At the heart of physics lies experimentation and observation. Scientists develop theories based on observations and use experiments to test these theories. If experiments agree with a theory, it strengthens our understanding. If not, the theory must be revised. The fundamental forces in nature, like gravity, electromagnetism, and the nuclear forces, are all part of the realm of physics. These forces act on everything we know and dictate the behavior of everything, from the fall of an apple to the behavior of light and even time itself. Units and measurements. Before diving deeper into the physics concepts, let's talk about the importance of units and measurements. Every field of science requires a clear, universal language to communicate results, and in physics, that language is the system of units. In the International System of Units, or SI, is the globally accepted standard. Let's take a closer look at the seven base SI units. Meter, M, is the unit for length, helping us measure distances between 2 points. For example, if you measure the height of a building, it's done in meters. Kilograms, kg, the unit for mass. Mass is the amount of matter an object has. The mass of an object is constant, unlike weight, which can change depending on gravity. Seconds, S, the unit for time. Time is essential in every aspect of physics, whether it's measuring how long an object takes to move or how fast a particle travels. Ampere, A, the unit for electrical current. It measures the flow of charge in a conductor. Understanding current is essential in studying electromagnetism. Kelvin, K, the unit for temperature. Temperature plays a crucial role in thermodynamics and understanding heat transfer. Mole, MOL or mole, the unit used to measure the amount of a substance. It tells you how many atoms or molecules are present in given samples. Candela, CD, the unit for luminous intensity. It's used when dealing with the brightness of the light emitted by a source. These base units allow us to measure physical quantities accurately. By understanding the relationships between these units, we can derive other units such as velocity, meters per second, ms, or energy, joules, or J. Understanding the significance of units is critical in physics because any small mistake in measurement can lead to vastly incorrect results. So, precision is vital. Scalars and vectors. Now, scalars and vectors are the most basic things in physics. For example, in physics, we encounter two types of quantities, scalars and vectors. These two types of quantities differ significantly. And understanding the difference is key to solving many physics problems. Scalars are quantities that only have magnitudes. In other words, they describe how much of something is there, but not the direction. Common scalar quantities include temperature. For instance, saying the temperature is 30 degrees Celsius tells you how hot or cold something is, but doesn't specify any direction. Mass. Mass tells you the amount of matter in an object, but has no direction. Speed. Speed refers to how fast an object is moving but doesn't tell you which way it's moving. Vectors, on the other hand, are quantities that have both magnitude and direction. They are more complex and are crucial in understanding real world motion. Examples of vectors include displacement. This is the shortest path between 2 points and it specifies both the distance and the direction. For example, 10 meters north describes how far and which direction. Velocity. This is the speed in a particular direction. For example, 60 kilometers per hour east gives both the speed and the direction. Force. When you push on an object, you apply a force. This force not only has magnitude but also direction. In physics, you'll often need to perform vector addition to combine multiple forces, velocities, or displacements. For example, if you're traveling northeast, you can break that journey down into two components, one traveling north and one traveling east. Graphical representation of vectors helps in understanding them better. When vectors point in the same direction, you add their magnitudes, but when they oppose each other, you subtract their magnitudes. Newton's laws of motion. One of the most significant developments in the history of physics came from Sir Isaac Newton. He formulated the three laws of motion, which are the foundation of classical mechanics. Let's take a look at each one. First law, the law of inertia. Newton's first law states that an object will remain at rest or continue to move with constant velocity unless acted upon by an external force. This is known as inertia. For example, a ball at rest will stay still until you kick it. Similarly, a ball rolling on a frictionless surface will keep rolling forever unless something stops it. This law tells us without an external force, objects don't change their state of motion. The second law, force and acceleration. Newton's second law gives us a relationship between the force applied to an object and its acceleration. The formula is F equals to ma, where F is the force, m is the mass, and a is the acceleration. This law explains that the force applied to an object will cause it to accelerate, but how much it accelerates depends on its mass. For example, if you push a car and a bicycle with the same force, the bicycle will accelerate more because it has less mass. Third law, action and reaction. Newton's third law states that for every action there's an equal and opposite reaction. This means that if you exert a force on an object, the object exerts a force on you with the same magnitude but in the opposite direction. For example, when you jump off a boat, the boat moves backwards because of the equal and opposite reaction of your jump. Today, we've explored the core principles of classical mechanics, starting with the essential concepts of physics and moving into the fundamentals of measurements, scalars and vectors, and the three laws of motion. These concepts are the building blocks for understanding the physical world. In the next lesson, we'll dive deeper into topics such as the motion in 1 and 2 dimensions, work and energy. But for now, make sure to revisit these foundational concepts as they will be instrumental in our understanding of more complex topics to come. Thank you for joining this lecture. I look forward to continuing our journey into the fascinating world of physics with you. And have a great day.